Hi everyone, I'm Arun now. I'm going to talk about brand pasting, and it's based on two works that has been published listed here, and yeah, I'll just go straight on. The motivation for this work is the assay tension, which may or may not exist anymore, but there's been recent result that shows that there's tension in the assay parameter, which is a function of segment 8 and omega matter, that is different from the Planck CMP and the low redshift, large-scale structure probes, like galaxy clustering, cosmic sphere measurements, and also galaxy cluster abundance measurements. And it turns out that there's another way of measuring or probing segment 8 that is using the clustering power, clustering measurements of galaxy cluster on the sky. And this has been actually proposed a very long time ago by Komatsu and Seljack, where they are showing that when you measure the TSE angular power spectrum of galaxy cluster, so basically you're measuring the clustering power of any galaxy cluster at some particular angular scale, you are very sensitive to, but the amplitude of the clustering power is very sensitive to sigma 8 to the power 8, and also omega matter to the power 3. And this gives a very nice alternative to constraining cosmology compared to cluster abundance measurements that we heard in many talks in the previous few days. The good thing about the SE power spectrum measurements is that you don't really need mass calibration. You don't need to worry about hydrostatic mass bias. And it's also insensitive to the selection function because you're basically measuring all your signals on the sky, so you don't need to really go and select galaxy clusters as galaxy cluster counting experiments will need to do. So the reason that the angular power spectrum is a powerful probe of cosmology is because its amplitude is directly proportional to the cosmic volume, dV, dz, d omega, and also the mass function, d and dm. But at the same time, it is also sensitive to the astrophysics in the ASIAA because it also depends on the gas profiles. And in the case of the TSE power spectrum, it will be sensitive to the thermal pressure profile, for example. So to constrain sigma 8 from angular power spectrum, we also need to account for the astrophysics. So in order to address this challenge of accounting for astrophysics and cosmology with the TSE power spectrum, we developed this band pasting method. It is a very simple and physical model of putting polytropic gas in a hydrostatic equilibrium in a Darmstadt potential characterized by its mass, redshift, and concentration. And we also add in all the essential galaxy cluster astrophysics like feedback, star formation, Google modeling, and nocturnal pressure due to gas motions. So it's something like, well, this is a Xiaombao, where you have a dough, a dumpling shell that you can count it as a of the Darmstadt potential, and you are putting in whatever baryons inside the dumpling, and in this case, this is a chocolate xiaolangbao. So here I show how the varying the feedback and nocturnal pressure, especially changes the gas profiles in our band pasting model. So on the top panel, I'm showing the X-ray emission profile by changing the feedback. So the red is the highest value of highest feedback on the left panels, and also changing the nocturnal pressure. And again, red line meaning the highest nocturnal pressure, blue line shows the lowest nocturnal pressure. And you can see that if you increase the feedback, you're basically pushing the gas out from the potential, so you're lowering the gas density in the inner regions, you're decreasing the overall X-ray emission. And when you increase the nocturnal pressure, you're reducing the amount of X-ray emitting gas, which depends on temperature, so you're also getting a lower X-ray emission. At the bottom panel, I'm showing the same effect, but in the thermal pressure. So when I apply this to model the angular power spectrum, and here I'm showing that in sort of extreme cases of feedback and nocturnal pressure, how the angular power spectrum of TSE angular power spectrum behave. And the plot on the left shows if you increase feedback, again, because you're pushing the gas outside of the halo, you suppress your power at small scales, which is indicated by the high L value here, and you're increasing the power at large scales or at low L, low multiples. And on the other hand, if you are changing your no-throw pressure, if you increase the no-throw pressure amplitude, you're basically reducing the total amount of thermal energy in your gas, so you get an overall decrease in your angular power spectrum at all scales. And here I'm showing the maps which correspond to the band pasting TSE maps that correspond to these changing in the feedback energy and also the no-throw pressure. And here is basically the same thing, but showing in the X-ray surface brightness maps. So changing both the no-throw pressure and feedback also changes the X-ray angular power spectrum, but a bit differently than the TSE power spectrum. So with this model, we apply this to the ASIAA half-sky survey or half-sky map that's constructed from the publicly available ASIAA ERAS-1 release. And so the good thing about the ASIAA map is that it basically, because it's a half-sky map, it covers a very large area, which is good for the angular power spectrum measurements because it means that we can get a very low cosmic variance in our measurements. And to test our result, we mask out the Milky Way, ASIAA bubbles, and also nearby point sources that is indicated due to AGN and star-forming galaxies, and also nearby clusters to mitigate non-Gaussian errors. And so here's our sort of measurements. So the dotted line, the dotted black lines are our measurements of the angular power spectrum from ASIAA. So it also includes error bars, but they're too small to be seen. And so in the lower panel, I show the fractional error, so it's of the measurements. And this is very small thanks to the very large sky area. So we fit our band pacing model to the measurements, and the best fit line is shown in the blue line, and we additionally show the one halo term and two halo term of the power spectrum. And one thing to note that is that there could be contamination due to unresolved AGN, and we find that the unresolved AGN is actually very small. So we can actually derive sigma-8 from our measurements, and this plot on the left shows our estimation of S8, and it's actually quite consistent with Planck, so I think this is quite promising to constrain both S8, and also we are able to constrain other astrophysical uncertainty like no-throw pressure, which is actually, we find it consistent with our prediction from cosmological summations, and also we can have a constraint on feedback and other astrophysical parameters. So the measurements here, we show that there could be some systematic uncertainties that we haven't been carefully taken care of. So in order to do that, we try to do a forward modeling to see if we can look into some systematics that in both angular power spectrum measurements and also cluster counting experiments. So to do that, we use our band pacing model and paint it on the half-sky Wushu simulation for around with 75 million halos between redshift range of 0 to 2 above the group scale mass. So shown here is the half-sky map of the Compton line map and also the X-ray surface brightness map. And with the band pacing model, one thing that we can do is we can artificially change the shape of the halo, and we know that galaxy clusters are not spherical, they are triaxial, and we can investigate how this triaxiality impact our cluster observers. So this is a same halo in our map, but one is we apply triaxiality, and one is just a spherical halo. And here we are showing that, so we measure the LXM relation for both maps, for the triaxial map that we created, and with the map that is created with spherical halos. And we measure the difference in the scatter, and we find that the scatter, or what we call the extrinsic scatter due to projection effects and triaxiality, can account for half of the total scatter, in addition to the intrinsic scatter that Joey talked about in the talk. And for the angular path spectrum, we actually find that the intrinsic fluctuation in the ASIAA profile that has not been encountered in our halo model actually add in additional clustering signal. And that's because the intrinsic scatter between halo and halo in the profiles, it creates more fluctuation in both X-ray surface brightness and contact mine, so that boosts up the signal. And so ignoring those scatter can really underestimate the angular power by 10 to 40%. And looking ahead, we can also apply this fault modeling technique in band pacing to predict how changing physics like feedback changes the selection function, for example in X-ray. So I'm showing a small patch of the band pacing Wuxi map, where we changes the value of feedback, and you can see that if we change the feedback, you are getting less and less number of galaxy clusters that's shown in the maps here. So one application here we're doing is we are collaborating with the Fornex collaboration to form model how feedback physics, for example, affect the X-ray selection function. So here's my summary slide. So map level analysis like angular path spectrum, I think is a promising tool of doing cosmology other than cluster counting. We applied it to ERAS-1 path spectrum and get some constraints on cosmology and astrophysics. We used the band pacing map to quantify some of the map level scatter. You can download the maps and catalogs in the link shown here. And I think band pacing would be a promising tool to do fault modeling and also field level inference. So thank you.
Thank you. We take questions.
So nice talk, or nice result. So I know for the SC power spectrum, usually a lot of times the uncertainties on the predictions about SC power can vary by 50% or a factor of 2, just based on some of these things like uncertainties about non-thermal feedback. Are those effects, worse or less or more for this sort of similar analysis of X-ray? It's just because of also things with like, once you account for things like cool core formation and stuff like that, how does the systematic uncertainties vary between the two methods?
Yeah, I think my understanding is the current SC path spectral constraints, the most important systematics is the point source, the contamination from background or foreground in a sense, like point sources from dusty software galaxies, right?
Right, the CIB TSE correlation. Yeah.
So X-ray, as I showed, is also facing some similar systematics, like point sources from AGN. Although I showed that the AGN contamination is due to unresolved AGN is subdominant, but this is based on an extrapolation from deep measurements from EVATs, so there's still some uncertainty in that. So I think having some cross-correlation, say, between X-ray and SC may be the step forward to mitigate both systematics in SC and X-ray. So I hope I answered your questions.
Yeah, interesting. Yeah.
I had very similar question. So for their X-ray CL, and to get cosmology, you have to have the AGN contamination known. And you have said it's subdominant. How sure about that? Like, you must be extrapolating some model because.
So we are using HOD model to model the AGN and resolve clustering, and that is based on the latest measurements from the EVATs measurements. So in EVATs, they calibrate the AGN HOD model. So we use that to model the unresolved AGN component.
Yeah, but the EFEDS AGN and the ERAS AGN, if if you just look at, they look very different. I mean, in the sense like, have you tried to see if the EFS model matches with your ERAS? Because I tried it doesn't match. So I don't know.
So you were referring to the resolved AGM or unresolved AGM?
Unresolved, of course, you have to model it and then extrapolate, right?
Yeah.
The resolved region, the ERAS category. So if you look at the same patch of the sky and look at the number of AGNs in, it's just see the picture of the number of AGNs in ERAS and the AGNs in EFEEDS, the numbers are different and they don't be on top of each other. So I don't know what's.
Well, I think part of the reason is the EFS is much deeper than the ERAS.
For the same flux cut.
So, yeah. I think the difference is due to the exposure time, but I may be wrong.
I have a quick questions about the halo shape for the gas. So you mentioned you account for the shape for the gas halos. So do you assume that the gas follow the dark matter potential? Pressure follow the dark matter potential, so you assign the shape.
So in modeling the shape of the gas, we actually look into TNG 300 and we actually calibrate the shape between the gas and dark matter. So we're using that relation to paint the gas shape onto the Bragg panel.
Also, you do that for the substructure levels as well?
Sorry?
For the substructures as well?
So right now we don't really have structure in the Bragg panel.
Thank you.
How does this compare to the European baryonification, the baryonification model?
Baryonification model?
Yeah.
So it's the baryonification model, if I understand correctly, it refers to how the baryon affects the underlying dark matter distribution. Right? So it's a bit different because we are not directly modeling the dark matter distribution. We're just painting gas on top of n-body dark matter halos. So we are not modifying the dark matter distribution yet, but we do have we have implemented the, for example, the Steiner model based on the Brownian physics that we implemented. We actually have a way to change the underlying dark matter halo potential. But
No
I'm not-
feedback back to dark matter distribution. No feedback back to dark matter distribution. Right.
Yeah, we are working on that. Yeah, the back reaction on dark matter halo. Thank you.
Thanks, Erwin, for a very nice talk. Yeah. And we have our last speaker today, Jeremy Yang, talking about cool core, non-cool core diode